Okay, well, welcome to this first in the series of BPHO Computational Challenge produced by Dr. Andrew French. Just to point out, Dr. Andrew French has actually written a book about this stuff, which you could purchase, and it's advertised on the BPHO website and also on his Eclecticon. But that's by the by. So what are you expecting this evening? Well, I don't really know what you're expecting, but I can tell you what you should be expecting. An introduction to how you can do various projects in computing. There'll be one particular topic tonight, but it's not for you to understand every detail or follow every bit of code that's discussed. It's for you to get a bit of an overview. So you should certainly have some sort of notebook or paper with you so you can jot things down as they occur, but you're not going to have a sort of complete lecture course which you could sit as an exam afterwards. So there's nothing like that. You're getting the gist, the flavor of the exercise. So you need to make sure that you jot things down, which you can follow up later on a future occasion. So you're learning how you can be kind of wide-ranging in the sorts of things you can do, but you're not going to be asked to do all these things. And it's certainly not something you could accomplish within an hour. I think Dr. French has probably spent a few weeks on each of these topics. So you're getting the benefit of his hard work and his focus. So enjoy it, but concentrate and ask questions in the Q&A. The chat is for replying to sort of quick questions during the session. So use the Q&A and we will try and answer them as we go along. Please don't ask lots of questions about what's happening next week and things like that. All very interesting, but really let's stick to the point at hand. So if I can hand over to Dr. French, we'll start.
Thank you very much, Professor Hughes. Good evening, everybody. My name is Dr. Andrew French, and welcome to the BPHO Computational Challenge 2025. This is the 4th year of this course. So I'm going to speak for about maximum 10 minutes about what this course is, what it means, the project, how it's assessed, how you get gold, silver and bronze medals, electronic ones, of course, and what the kind of goal of the challenge. And then we're going to get straight into the first session. So we've got about 10 sessions, and each of those is an aspect of physics. This is a physics course, but how we can look at the world of physics with a kind of computational and model building lens. And that's kind of the main theme of this whole exercise. So let's go and have a look. So the what and the how first. Okay, so hopefully if you're here, you've obviously registered at bph.org. And we will send you a Zoom link each week. So we've got 10 weekly seminars. All right. I believe you've also been sent a link to the BPHO website. Some amazing stuff on that. And I have my own website, the Eclecticon. I'll give you a sort of visual tour a bit later. But we have a special page for this course. All the resources you can see here, you can download. So we've got an annual challenge, which will be set sort of late March, early April. It's a top secret for the moment. Don't ask me what that's going to be. Although if you go back to the last 3 years, you can kind of, by process of elimination, work out what it's not going to be. So if you're brand new to this, the first year was all about modeling the atmosphere. The second year was about solar system orbits. And last year was about projectile motion. So what we're going to do is sort of build you up, give you some inspiration for dusting off some programming skills, or perhaps starting programming yourself. You can start absolutely from zero. The idea is to inspire you to do it from your experience of physics. That's the point. In order to sort of do this, give you a little incentive, we're going to set a challenge. And this isn't like an exam. This is quite different. You've got about 3 months to answer, but it's really tasked. I'm going to set you about 10 or so tasks, which get progressively more complex. And you're going to put that together. You're going to write, you could do it in Excel, you could use MATLAB, Python, or any, in fact, it doesn't really matter what language you use, as long as you do something computational. And then you're going to put that together as a 3-minute YouTube video. And that's going to present your solution. And we've had some absolutely fantastic videos in the past few years. So the very best, we will select the top 5, and you will get a special award at the Royal Society. which is part of the BIFO Awards, which will be happening in a few months' time. So alongside round 2 and the Olympiad teams and all the other things that the BPHU do. Okay, so there we are. So that's we've upped up the time because the challenge this year is a little bit longer than previous years. We're seeing some progression here. So there we are. It's assessed by a 3-minute YouTube video, and you can do it individually or in pairs. But I'm afraid that's the limit of the groups. Okay, so there we go. Any questions on what is this challenge before we talk about why we're doing it? Has anything appeared in the chat already? No? Am I still broadcasting okay, Nina?
Yep, you're still clear. It's just
all good.
Fantastic. All right. Okay, so firstly, why are we doing this? So here we go. This is The Bookkeeper by Van Dyke. I have a quill, some paper and a sand timer. What could be more useful? Well, maybe some central heating. It looks like he's wearing a duvet there. But in the modern era, think of a modern profession that does not involve the use of computers to create, record, store information, control machinery. I'm not really sure I can. Even sort of sports, you're going to be involving computation in some sense. So, this is the world that we're living in. And wouldn't it be better perhaps to be active in that process? So, I've sort of had experience of data flow, data processing, information presentation. So you've got a little illustration at the bottom here. This is a pendulum. Look, I've got these things nicely labeled: the length, the angles, the velocities, the mass, the height. All right, you do an experiment in the lab and you might put that into an Excel model, or you might actually predict mathematically how that pendulum is going to move. Maybe the angle versus time, for example, maybe the velocity versus time. Or you might just measure these things. You might measure period versus length. In fact, that's what we've got the graph here for. And so you'll make some measurements, and then you might want to analyze that. You might want to write an automatic recipe which takes the data and creates a graph with error bars and all the things that might be laborious for you to do repeatedly, but a computer can do in a fraction of a second. So in some of the basic things, going from the real world, a model, to data, to graphs that look good that you can publish, that really is the guts of how most professional physicists and scientists will work. All right, so we're going to kind of lift the lid of this process, and it might be slightly different to how you've experienced school science, because you've been, as it says here on the slide, you're probably mostly doing some problem solving, taking some notes, performing some lab experiments, but perhaps you've not really appreciated that exactly what subset of that is what you're going to be doing after you leave education. All right, so I think it's important to kind of understand where we're going with this, because we want all of you to keep going with physics forever. So real scientists spend most of their time on this: data flow, data processing, and information presentation. So start learning these skills and you're more likely to get a job, basically. So if you look at the largest companies in the world at the moment, you probably think of things like Amazon or Google or Uber or Meta, Tesla, Netflix. And these companies, and there'll probably be different companies in the next few decades, and these will disrupt the traditional industries. And all of them have are really embedded with the use of information technology. So, if you don't have these skills, you won't have much to offer these guys, no matter what kind of degree levels you get. So I think it's really good for your future investment, but also I think your enjoyment of physics right now to start learning these skills. And do not worry if you have never done any coding before. That's the purpose of this course, is to give you some inspiration to get started. So there we are. Even if your horizon is, how can I get a distinction at A-level and get into a top flight university? You think, well, that's all I care about at the moment. Scientific computing, if we can call it this, is a really good way of consolidating your subject. As Professor Hughes very kindly alluded to, I have a little book out called Science by Simulation. And one of the 3 tenets of this book is that if you build mathematical models yourself and code these things up, it's a really good way to understand the physics you are doing. So I'm teaching projectile motion with my 4th year, so my lower 6th at the moment. And in fact, that was the BIFO challenge last year. So we'll do some work on throwing balls and working out the trajectory to hit a particular target. Once you've done a few problems, what you want to do is code that up. And in fact, if you want to have a look at all those possible things you can do with projectile motion, have a look at the challenge last year. And also, it's rather fun. If you create something, that's a really good thing to do. You can take as much time as you can over it. Right, so there we are. If most future jobs currently performed by humans will be done much more efficiently and safely by robots, or perhaps even AI, wouldn't you want to be the person programming this technology? I would rather that than being the programmed or just a consumer. All right. So there we go. We may have a dystopian future ahead, but if you're one of the programmers, I think that's a good investment for the future. So there we go. What's going to be the menu of the computational physics course over the next 10 weeks? So very shortly, I'll get some more questions, and then we're going to get into modeling motion. So kinematics, and I think I've got about 10 examples of various programs and things that I've done over the years that you could have a go at yourself. And of course, pretty much everything I'm going to talk about you can download from my website. You'll need to get MATLAB, but you could translate it to other languages if you wish. And then we're going to work way through basically a kind of tour of physics, really. So week 2, we're going to look at sort of models, experiments, data analysis. Week 3, gravity and astrophysics. Might not actually be this strict order. I'll have to check. Maybe gravity will be week 2. Then we might look at waves and optics. 5, things like quantum mechanics, nuclear physics, radioactivity, electromagnetism, and then things like special relativity. So that's if you haven't studied that during your school course, that might be a fun one to have a look at. Thermodynamics, and then we might get into things like chaos theory. Epidemiology, which is all about diseases. So a friend of mine, called Dr. Klern, we published a paper on epidemiology about the plague of the village of Eyam in 1666. And it's rather surprisingly for everyone, of course, then COVID struck a couple of years later. So what we learned about epidemiology was actually very useful for our school's response to the COVID pandemic. So some of these things, you do things for fun, for your own learning, and then who knows how useful it might end up being. Once we get to about week 9, we will release the challenge. Okay. So I think that's, before I talk about some resources, do we have any questions? Nope. Am I still coming across okay?
Yes.
Yep.
Excellent. Right. So firstly, we've got the BPHO website and links there. I'm pretty sure you've already got onto this in order to get onto this course. So we have a special page, and we'll be updating that shortly with videos and links to various things that I talk about. And in fact, when the competition is actually released. So there we go. So there we are. I think that's obviously a bit out of date, 14th of August 2023, but somewhere in mid-August 2025 will be the deadline for the competition. So you've got plenty of time. Okay, so this is Science by Simulation. Essentially, this is my book, and it's this one, the first volume. It's going to be a volume. It's be a 3-volume series. Volume 2 is in the works. It's going to be out hopefully within a few months. And it's models of classical physics. So I think quite a lot of what we'll talk about today will be in volume 2. But things like the epidemiology and other aspects of applied maths are in this book. So if you're interested in radar, if you're interested in high frequency trading, if you're interested in diseases and chaos theory, all the kind of recipes will be in this book. All right. So there we are. And here is my website, the Eclecticon. There's all sorts of things on this, lots of physics. And as you can notice, there is a BPHO direct link and also to the book itself. So there we go. And in fact, under the physics courses part, you'll see a direct link to the BPHO computational challenge page, which you will better find out yourself. So I'm just going to start on the first part, which is on modeling of motion. Let's go and have a little look at this. So kinematics is pretty much where everybody tends to start when you're doing a physics course. All right, it's probably one of the oldest aspects of using what we now call science to have a look at the real world, making observations, making theories about what those observations mean, and then testing those theories, with reality. I mean, that loop sounds obvious to us, but that, of course, wasn't obvious at all, at the time of Aristotle, etc. So we're going to start off, and this is how I tend to start off mechanics. So those of you, if any of my students are on the call, hello, you will have seen this at some point. So this is still the world's fastest man. This is the great Usain Bolt. And I think this is still the world record, 9.58 seconds for the 100 meters. So when we're talking about kinematics, the study of motion, you want to do a one-dimensional version first, a straight line. And then you can talk about 2D projectiles, and then you can get to 3D motion, etc., etc. And then have some fun with space and time when you do special relativity. So when you talk about motion, you might say, well, what does that mean? And so you might plot a graph like displacement versus time. So that's the sort of simplest thing you could use a computer for, is actually to represent how far Usain Bolt has gone in t seconds. And so I've made a graph here, and I've used a cubic spline, which is a graphing tool that MATLAB uses and others, and it fits cubics between the data points. And you don't have to do any work apart from to call the cubic spline function. If you use Excel and you have a nice smooth curve, it's probably doing the same thing. So you really appreciate, if you're new to this stuff, that there's all sorts of tools for display and analysis that are in the box, which are based on the programming language you've got. So I quite like MATLAB because that has a very, very well established sort of scientific toolbox. But Excel is also very, very good and mostly free for a lot of you as well, if you've got a kind of school login. So what are we looking at? We're looking at the two races in 2008 and 2009 when he both broke the world record. And in 2008, infamously, he sort of raised his hands in the air before he crossed the line and broke the world record. So who knows how fast he would have actually gone. Although, of course, we could use the data here to actually maybe predict that. The bottom, I think, is a screenshot from the London 2012 Olympics. Anyway, so it looks a very similar graph. There's not much we can tell about that. Possibly the gradient gets steeper as time goes on. So what you can do is you can look at your cubic splines. So you're fitting cubics between your data points. And then you can, actually a question, how many data points do we need to define a cubic? Let's put the answers in the chat. I'll give you a few seconds. Right. What's coming in the chat, Nina?
Yeah, we're getting lots of threes. 6,
Ooh,
9, 4,
6,
but threes.
Right, excellent. So if you think of cubic, so x cubed plus bx squared plus cx plus dx plus e. Sorry, oops, I missed one there. So we're going to need. So if you think about all your terms, 3 to you've got the 0th term, so you've got 4 here. It's not just 3. You've got 3 terms from your powers of x plus your 0, so 0 to 3. So you've got 4 numbers, the coefficients of your terms. So basically every 3 points is what we need. So there's not many data points here to plot some cubics, but there we go. So right, so what we can do once we've got a cubic, for those of you who've started calculus, if we get a cubic, we can differentiate it and get a quadratic. Or if we have loads of data points, we could just draw lines between each one and work out the gradient of those triangles. But because it's a cubic, a nice smooth series of curves, we can do rather better than that. And we can work out the gradient at any point along that line of displacement versus time. So this will be a numerical method of doing calculus. You've got some data, you plotted a graph, what's the gradient at any point? And that just opens up a world of all sorts of possibility. So if you've got displacement versus time, I can now work out speed or velocity versus time in a particular direction. So this is what I've done. And to illustrate this, imagine we were looking at a time, it's about 3.7 seconds, something like that. And I draw an enormous triangle at a tangent to my curve. And delta x over delta t gives me my local velocity, which is 11.2 meters per second. So if you're doing your GCSE exams, you almost certainly will have done that with a ruler. All right, but that'd be very tedious to do for 1,000 points along this. So we can get a computer to do that in a fraction of a second. So if we achieve this, and this would be a lovely thing for you guys to write, we can get something like this. And now that's much more interesting. So we've got a velocity time graph. It's in the middle of the three graphs of kinematics. And I always think this is what you want to start with when trying to understand motion. So the gradient of this graph is the acceleration, and the area under this graph is, of course, how far you've gone. All right. Caveat, if it's below the axis and we're talking a displacement, obviously that counts negatively. So if we compare the two races, it looks like he's accelerating. In fact, the acceleration gets larger, and then he reaches a point at about just before 3 seconds where he seems to sort of stop accelerating, and then increases the speed a little bit, and then maintains a constant speed for about 3 or 4 seconds, actually. For the 2008 race, you can clearly see he then loses about nearly 2 meters per second, which is he's basically a braking effect. He's throwing his hands in the air and having an aero braking sort of situation, and still breaks the world record. Whereas I think his coach may have had a strong word with him. So in 2009, his velocity is effectively constant. And this, if any of you are interested in athletics, and I may have revealed my personal interest in this, one of the kind of myths, I suppose, is that people pull away from the other athletes, whereas actually what's happening, that top class athletes will maintain their speed, and other people, sort of lesser athletes, if you like, will start slowing down. And Usain Bolt, for sort of almost 6 seconds, well, let's call it 5 seconds, is maintaining an absolutely outrageous speed of 12 meters per second. What's quite interesting, though, is to actually look at the little hump in the red line, the 2009 race, and it seems like he's slowed down a bit. Now, that may well be some just noise in the data, so it may not be real, because we've only got, about 10 data points. So it was recorded, so a very nice, I think, an Australian gentleman. Lasso, I don't think I've got his name, so I do apologise if anyone who did this is on this call. But he basically recorded the times, looked at the video, because there's a line every 10 meters. But in principle, you could record it every centimeter if you were looking at a film very carefully. So we don't really know if he was slowing down slightly, about 3.2 seconds. But it's kind of tantalizing to think that if he didn't do that, would he have reached 12 meters per second before 4 seconds and maybe got under 9.5 seconds? We'll never know, but there we go. In principle, you could use this curve to maybe predict what Usain Bolt could have done if he'd have run an absolutely perfect race. So there we go. Now, if we take the gradient of this curve, we get the acceleration versus time. And now we're starting to lead into Newton's laws. So, of course, mass times acceleration is the vector sum of force. So we can start thinking about, well, what forces are acting on Usain Bolt and, therefore his muscles, how much sort of stress they're applying. So you can start thinking about physiology and open a whole world of, strength training, all that kind of stuff, just from this data. And if we're not talking about runners, maybe we're talking about cars or aeroplanes or bicycles or the dynamics of insects, or in fact anything you like. And you can start to relate the motion, which you've got data for, to the internal forces and, of course, the external forces acting upon them. So we see a situation here where we've got the acceleration starting off at about 1 meter per second squared. So we've kind of had to assume that he blasts out of the blocks at about 4 meters per second. Obviously, he will have started from 0, otherwise that would be a false start. But we're assuming that happens too fast for our sort of measurements. But he then reaches at about 5 meters per second squared. So about half a g is his maximum acceleration. And then you can see the deceleration for the 2008 race. So a lot of it so far, we've used calculus or numerical methods to work out gradients, but also I've used a computer to plot all the graphs. So again, the axes right. So this is not just cosmetics. This is presentation of information to make things clear is one of the main kind of arts and crafts of STEM, I suppose, in terms of particularly for physics. So a lot of computer languages will really give you all the control to make your graphs as clear as you want in the style that you want. Excel's a bit more tricky to do this. So I recommend, particularly if you have an artistic bent, to try and code your own style. Okay, so and here's another example of this, is that when I'm sure your physics teachers go on about this all the time, that we need to use the same timescale to compare your graphs. So here we go. We've got exactly the same timescale for displacement, velocity, and acceleration. And then we can compare, we can contrast the kinematics. So there we go. So that's sort of example number one, how we might lead into this. Do we have any questions before I move on to something else? No, am I still broadcasting? All right.
Yeah, all good. We're dealing with the
Excellent.
questions.
So, okay, so kind of keeping with the kinematics theme. I think this is the news, actually. I think Blue Origin may have gone into orbit. I'm not sure it landed quite perfectly. So perhaps Mr. Bezos will stand sort of rather glumly next to Mr. Musk in the current US presidential inauguration with their sort of internal space race rivalry between them. But the Blue Origin launch, which I think contained Mr. Bezos, was on the 20th of July 2021. And quite a beautiful thing, really, in terms of how it was going. In fact, it's even more beautiful if you actually look at the telemetry data, which I can't remember if I actually sat. I think I probably sat with the video and geekily encoded this sort of every few seconds. You can watch the video and it tells you the height of the rocket. So I put this into a spreadsheet, and then we can see. So I've done this in Excel, and I've got altitude, velocity, and acceleration. And what I've done is I've used a numerical method for calculating the acceleration from this. So I think the velocity was given, yes, I think this is probably taken from the video. So I've converted that into meters per second from miles per hour, and my height in kilometers from feet, because it's American. And then what I've done is I've done a numerical derivative, so the gradient at any point. And as I hope you can sort of see here, I'm doing the difference in velocity divided by the difference in time. So none of the sort of fancy fitting of cubics that we did for Usain Bolt. We've got quite enough data here to do something quite simple. Now, as a result, you get some rather noisy acceleration, but you've got some interesting remarks here. You can see that it's pretty much at G, sort of where I looked at the arrow. So actually towards the top of, the sort of near apogee, the idea that there's a sort of, it's essentially weightless. So, it's falling at the same acceleration as gravity. So, the experience of the astronauts inside your little sort of capsule will be equivalent to being in free fall, and therefore they will feel weightless and float around. So there we go. And of course, then you can sort of see the acceleration in the negative sense. So the acceleration is going downwards, and you can sort of see taking about 4 Gs at one point. So that might not be so comfortable. You can also sort of see how linear the velocity time graph is for much of the trajectory. And of course, then you can relate that to the altitude versus time, and they are reaching just over 100 kilometers. There we go. So here we are. Here's the sort of like a zoom in of the pictures, and this is the team. There's four of them in the capsule. So there we go. Maybe that's the future of space tourism. So here we go. So kinematics. It provides a really good reason to wish to know velocity or acceleration from displacement measurements. All right. So, that's what kinematics is about. We really want to know the velocity time graph or the acceleration time graph. That tells us what the forces are, etc. So the gradient of the underlying curve. And of course, if we can find a gradient in for kinematics, we might want to find a gradient of other things. Maybe in chemistry, for example, the rate of change of the concentration of a chemical. That unlocks the world of physical chemistry. You might just want to find dy by dx, for example, for some function that you are trying to differentiate, all sorts. So there we go. So there we are. So for Bolt, we fitted a spline. And for the Bezos example, we just did something a bit more simple. We sort of drew a straight line between the data points and worked out the gradient. But either way, in both situations, we've told the computer how to do that, and then we've run it. All right, so there we are. Okay, so here we go. Something completely different. So your kind of next thing in mechanics, you might want to look at maybe collisions and maybe ball bouncing, that kind of stuff. So a bouncy ball bouncing off the ground. I'm going to go and show you a little simulation of this, and then we'll kind of talk about the mathematics that's on this screen. So here we go. So we got a bit of live programming. Actually, this is a bit more fun. This is the 2D version. I'm going to run this first. Just a little notice here, if you've never done any programming, I won't go into too much detail here, but I'll just note a few things. So whatever programming language you use, you want to have a kind of development environment. The text I've got here, all programming languages, is you will basically type some text, some instructions for the computer to interpret. And most modern languages you can actually understand as a human, and then the computer translates that into a language that the computer can understand and hopefully run nice and fast. That wasn't always the case. The best thing I think you can do when you're trying to write a program is start off with a commentary. And that's the computer ignores this entirely. So in MATLAB, this is green preceded by a percentage mark. Can anyone tell me what that is for Python? How do you get comments in Python?
Yeah, people are saying a hashtag.
Yeah, it's a hashtag. Does anyone know what it is in JavaScript?
Oh, there's so many answers, so double slash.
And so every language had its own commentary thing. It's quite amusing. So MATLAB uses a percentage sign. So this thing here, the function balls in the box, basically creates a sort of part of memory. So if I run this thing, nothing will appear in my works. So if I define a variable a equals 1.23, that's defined in my workspace here. And if I say I could square that, a hat 2, so I can use, a language like MATLAB as a glorified calculator, but it does so much more. And you can see the variables have turned up here in this workspace, and I've got a little folder where I can run things. But if I run balls in a box, for example, I've got, hopefully you can see this all right. I'll just make that slightly bigger. It should repeat once it's finished. There we are. So what I've got is I've got 2 balls or 2 circles, which have random velocities and with a little bit of friction. So it will lose a little bit of energy. There's a coefficient of restitution here. I think it's after 10 seconds it should repeat. There we go. So they're kind of bouncing off each other and the walls. And I guess it looks relatively realistic. Looks quite complicated, doesn't it? With all these different collisions, this is like the worst BFO problem ever. Why do we want to solve this? Well, I'm not having to solve it. The computer is doing it for me. And actually, the code for this is actually very, very minimal. So, in fact, most of the code of this is actually displaying the square itself and plotting things and updating it in a smooth way. So the whole code for this is 160 lines, and quite a lot of that is commentary. So just an example, when I'm writing my code, I will define all the commentary first. Like I'm defining the various bits, like the strength of gravity, the coefficient of restitution for the ball to wall collisions, other inputs like the ball radii, and I got things like plot initial scene, plot square box. So I kind of think through the problem itself, and then you write your commentary, and then you can kind of look up, if you're new, what's the code that does that thing. And that's a much more fun way of learning a language. So let's go and have a little look at the bouncy ball one, which I think is, so you can download all of these from the Eclecticon. So we'll go for ball bounce. I think it's this one, I hope. Let's have a look. Yeah, there we go. So we've got a little video. This is a bit more laggy than the other one, so I could update the display system. But we've got a model, an animation of a sort of bouncy ball, and it's dropped from the top. And as you can see, it doesn't bounce to the same height. It loses some of its kinetic energy every time it bounces. So how could we model this? And importantly, the graphs that were produced right at the beginning. So if we just run this, I'll load this up. So this is what it looks like. Not so many lines, this one. This is just over 100 lines. So let's just deconstruct all the essential elements of this. If we go back to the presentation, I'll slowly walk you through this. So what we've got, this is a numerical model. And yes, you can predict what's going to happen at t seconds later. But sometimes that's actually quite hard to do. In this case, because we've got the bounce. So what we can do is use a loop. And this is one of the most powerful sort of simple techniques that you can do with computing. Because what you've got to realize is that the human mind is, is the best computer ever, right? We've got more connections in our brains than there are sort of atoms in the universe, that kind of thing. We can do things that computers can't even hope to do at the moment. However, the number of computations per second is woeful compared to what an average calculator can do. So most chips work at, multiple gigahertz, billions of calculations per second are possible, even with modest computation. So if we can tell a computer to do something dull, but reliably fast, that's how to get the superpower. And perhaps my personal philosophy is that how we can get best use of computers is rather than getting computers to behave like humans and humans to behave like computers, it's best that we kind of stick to what we're good at, I think. Maybe this will save us from our AI dystopia, perhaps. So what's going on here? So what we've got, we start off with, so X is going to be the displacement of my ball. And you can see what happens on the graph here. And V is going to be the velocity, and positive velocity is in the positive X direction. So you can see that the velocity gets increasingly negative until it hits the ground. T starts at 0, we've got G, and then we've got an element of time, dt, delta t. So what I'm going to do is every 0.01 seconds, I'm going to compute what happens next. So I'm essentially dividing this up into little bits of time. And that is kind of one of the kind of key ideas of how to do mechanics, because not everything you can do, if you've done a bit of calculus, will know that to get displacement velocity, we integrate. But what if your velocity time graph isn't the sort of thing you can integrate, if it's a function that you don't know how to do? So you can get a bit stuck there. However, it doesn't matter. As long as we know what the acceleration is at any point, we can work out what happens next. So let's have a little look. So this is constant acceleration motion, which is nice and easy. So if you look at the inside the loop here, so I'm saying, okay, until my bounce number exceeds the maximum bounce number, which I'm going to set to be 50. So my bounce starts at 0. So that's true. What we do is we keep going around the loop until that criteria at the top is not satisfied anymore. So what I do is I add an extra element to X. Now, what does the xn+1 mean? I'm just going to pop out of this and show you what that looks like in MATLAB. See, MATLAB stands for Matrix Laboratory. Whoops, you can see me now. Which is, so everything is a vector or an array. So if I type X equals 1, 2, 3, okay, with square brackets, different languages have different notation. That creates a vector of 3 elements. So X2, for example, will be 2. All right. X3 will be 3, etc. All right. And so if I say X4 equals 4, I've now added an extra element to that array. And all that kind of stuff with vectors and things are all built into MATLAB. If you're using Python, it's something called NumPy, which sounds a bit like MATLAB in many ways. But it's quite nice to use a language which has all the sort of mathematical objects built in already, so you don't have to create them. So we go back to the presentation. Let's have a look at this one. So what we've got, if you have a look in the bracket here, what I'm saying what's the next element of X? So I started off with this one. What's the next one along? And so so X is ut plus a half at squared, constant acceleration motion. But remember, I'm taking away from X because my velocity is going to be so it's positive in the upwards direction, if you like. So basically, I'm taking away some of that in this particular case. And I've got my half gt squared here. So I'm measuring X from the bottom, right? So I need to take away my velocity. So v delta t is the distance traveled at constant speed downwards. So I take that away from X. But I've also got acceleration. So half g delta t squared is the distance traveled from acceleration due to gravity. So I've got those two parts, ut plus a half at squared. That's what I have to subtract from my displacement. So there we go. I'm working out what happens next, and I can work out my velocity, which is my previous velocity, plus g delta t. So because it's accelerating. So, and then I can increment time. Now, what gets interesting is when it bounces. So how do I check that we've got a bounce? Well, xn+1 is now going to be negative. So let's see, we've worked out what happens next, and we go slightly below the axis here. So a negative displacement. And also that my velocity is bigger than 0. Now I need that second term because once I've had a bounce, my X may still also be negative and I'll be stuck in an infinite loop. So one of the art of coding is to sort of prevent that happening, because the computers aren't very clever. It will just follow instructions. The and is a logical operation. So these two things must be both true. It's an AND operation. If that's the case, I'm going to add 1 to my bounce number, and I'm going to reverse my velocity. So the next velocity in my array, in this graph, if you like, in the table, will be the previous one with a minus sign and multiplied by my coefficient of restitution. So speed of separation divided by speed of approach, and that's going to be 0.8 in this case. And you can see, because it's actually losing height. If c was 1, then we would just keep bouncing at the same amount, rather unphysically. And I'm also going to add 1 to my my counter. All right, so because I've defined relative to n, so I need to make n plus 1. There's lots of other ways of doing that, but that's sort of keeping it nice and clear. So it may not be the most efficient way of doing things, because I have to do it round a loop, but hopefully you can see that that looks a bit like the physics you will have done in your classes, except rather than half gt squared, we've got half g delta t, and that's a very small number. So this might be thousands and thousands of iterations, but that happened very, very quickly. Quite a fun thing to do is to work out the time to stop bouncing. I'll show you some maths in a moment, but you probably want to look at that in slow time. And if we record the time it takes for a ball to bounce, we can invert our formula here to find out the coefficient of restitution. So that's a nicer way of doing it without a high-speed camera. x1 is obviously the initial height, so 1 meter in this case, and there we go. And the commands at the bottom, have you noticed that I've got almost as many plot commands as I have the sort of the guts of the physics, and that will vary from language to language. So, you know, a couple of these, num2 stir is turning a number, coefficient of restitution, to a string, which is something I can use to create the title. All right, so in MATLAB, titles are things called strings. Python is particularly good in the way that it deals with text. So there we go. Do we have any questions on this little simulation? Nope. Am I still coming across okay?
Yes.
Excellent. Right. Okay. I think I will skip over this one mostly, but I just leave it as a sort of thing to think about. Is that you can get this from the eclecticon actually, but this is how you can work out the distance travelled by a sequence of bounces. So what you do is you sort of work out, here's my height there, and c squared, because my speed goes as c root 2gh. So the height you do, if you do conservation of energy, there's sort of a nice Olympiad problem you can have a look at. So the height next is actually the coefficient of restitution squared times the previous height. So what you end up doing to work out the total distance travelled is you're adding a geometric progression, a geometric series, which you can sum. So that's the total distance you travel, but perhaps more useful is the time version, which is this one. And so if you add up all the times, then you actually end up with the total time of bounce, which if you rearrange, you can use that to find out the coefficient of restitution. So that's what was coded up in this bit here. So that's a really nice bit of maths to do once you've kind of mastered this problem. Okay, so here's another nice, a really good one, which is a classic example. Is when you drop a basketball and a tennis ball at different masses, and what happens is that the tennis ball fires up in the air. And if the ratio of these masses was infinite, in other words, m is infinitely bigger than little m, and all the coefficients of restitution between the basketball on the ground and the little ball and the basketball, if those are both 1, so elastic collisions, what you find is this will go up 9 times the original height. And it's possible to sort of work this out. So that's involving the 2 types of coefficient of restitution. And if they're all the same, you get this sort of example here that the height that it gets to over little one is less than this quantity, which if the ratio here is 0, so m is much, much bigger than little m, that's 3 squared, so that's 9. So you can kind of make a calculator for this. So actually maybe the first thing you might want to do actually, rather than actually getting into Python or MATLAB, is to dish out Excel and actually, you've got a formula, which is not, you don't want to be typing that into a calculator, that'd be tedious. So you could build yourself a calculator for working this out. So here's the general formula for this. So I've got my 2 coefficients of restitution, the basketball on the ground and the basketball and the tennis ball. And I've kind of made up what those might be. I've got my masses, my drop height. So my inputs are all color coded, and my outputs are in green next to all the text of what those numbers mean, and including the unit. I've got the equation here as well, and I've got a little picture of the situation which you can draw onto Excel. So, as simple as it may be, Excel is brilliant for making yourself a calculator. So, you could do a speed, distance, and time one, or anything. In fact, next time you meet a new equation, maybe build yourself a little calculator, and that will really get you. It's a great way of revising it as well as helping you to do problems. So here we go. There's a lot of maths here. I think, the formatting's a little dodgy for this page actually, but you can go onto the Eclecticon, and that's you can sort of follow that in slow time. All right. Okay. So this is an example of an app. So it's a bit more complicated than just making a small bit of code, because you're building a graphical user interface. So this is a situation where we're looking at collisions in 1 or 2 dimensions. So you saw the little demonstration earlier, and in fact, this is the sort of the physics of this is beautiful. You use something called the zero momentum frame, which is where you can do before and after has total zero momentum, and you can work out what that velocity is. In other words, you're running past the situation with a velocity big V such that the momentum is 0. And that velocity is actually the weighted average of the velocities of the 2 different objects. So what you do is, when you're in that frame, you basically reverse what happens. So that's also conserves momentum, and then you shift back into your laboratory frame. So this is actually the results of a collision. So there's your initial velocities. The bold font means a vector. You subtract your 0 momentum velocity. You reverse it, multiplied by the coefficient of restitution, and then you add that again. So that's what happens next. So every time you touch, you can work out what happens using this formula. There we go. So that's how conservation of momentum works. And that is embedded within this little program here. So I use this to set problems, for example, and you can kind of hide the velocity afterwards. You could even hide the masses. You could set a problem this. So it's a way for teachers or for students to setting yourself problems and then having a go, and you can sort of see what happens next. So this is the red ball and the green ball coming together, and this is what happens. Okay, so there we are. So, but an app is useful because it gives you everything you want and nothing else. What have we got? There we go. Some other pictures for this one. I'll skip over that. So here's another app which I use in my teaching when we're looking at Newton's second law. So mass times acceleration is vector sum of force. And certainly if you want to get into the kind of gold areas of the computational physics challenge, some of the best entries we've had in the last few years have written apps, or people have written kind of apps within websites, mobile phone apps, all sorts of things. In other words, something with some user interaction. So here we go. I think I should demonstrate this. I think we've got some time. So I'm just going to run this one. So I've got some physics here. Let's go for apps. Let's go up a level. There we go. So where we are, we've got apps. So we are. So here we are. We want slope, I think. There we are. They've got exciting names. Right, so here we go. So this is my former cat, Sybil, sadly no longer with us. Sliding down this slope here. So we've got 4 vectors acting on this. We can actually calculate the forces exactly. So the weight of the cat is 39.2 newtons. That's the purple sort of magenta arrow. And we've got the normal contact force, a kind of rope tension pulling the cat up the slope, and we've got some friction here. And if we do the vector sum of force, we can use our computer to actually work out what that vector sum is. And you can see that it's not a closed polygon. So if I show the mass times acceleration, we can see the black arrow going down the hill. So MA is 4.48 newtons. So the cat is accelerating. Now, if I increase my my tow rope, if I make that bigger, you can see everything else calculates. My graph dynamically changes, and you can see the mass times acceleration is getting smaller and smaller, and eventually we get to equilibrium. There we go. And in fact, now the text changes. We've got a closed polygon, and everything else moves. I can fix the axis scale to make that a bit easier. There we go. All right, and eventually your friction will start to reverse. And now Kat's still static, and now she's accelerating up the hill. Okay, so this is sort of a sort of inclined plane problem that will most people in the lower sixth will encounter this kind of thing, resolving the forces. You can in fact see the x and y components. So x is going up the slope, y is perpendicular to the slope. So all the kind of calculations that you would do are baked into the program, and you can explore things by changing these edit boxes and typing in numbers. So there we go. That's a kind of example of an app. This is a water rocket model. I think the text is too small to see, but this is another kind of loop. And this is a situation where Newton's second law is too difficult to actually do calculus with. So mass times acceleration is the thrust minus the weight minus the drag. And I've got the velocity times the modulus of velocity. Why have I got that? It's because the drag will follow the direction of motion. So if the velocity changes sign, in other words, you're going downwards, all right, I need to actually change the direction of my drag. So that's not something that you can do integration with very easily. Also, the weight is going to change because the mass of the object will change because we're losing water. This is a water rocket. So here we go. So the mass I reduce by factor mu, which is kilograms per second, between 0 and when I've got rid of all the water. So the mass of the water divided by the mass ejection rate. And after that, it's a fixed mass of the rocket. So this will be quite difficult to actually do, but I can do it in a loop. I don't know if you can kind of see in my presentation, if I can zoom in a little bit, what you can see, we've got a loop here, and I've got some sort of an if statement, which is how much mass of the rocket do I talk about? And then I've got, a ut plus a half at squared. So what I'm doing is I'm using constant acceleration motion within time steps to find out what happens next. Although my acceleration is driven by this equation here, where loads of things are changing. So you could have the most complicated equation for your dynamics. The forces could be electromagnetism, all sorts of stuff. But if you use constant acceleration motion within time steps, you can work out what happens next. And, even if we can't do it analytically, i.e. use a computer to find out what happens in t seconds, we can do it every delta t and do it in a loop. All right, so that's kind of a powerful idea. So I think we're coming towards the conclusion now. I think I've got one more to show you, but do we have any other questions before I show you the final example?
All good.
All good, fantastic. So anyway, here's some. So here's the actual rocket model. We timed the launch of our rocket. So that's where the 7.58. I've got rather too many number of decimal places here, but it's about 7.6 seconds it was in the air for. So we were trying to work out how high the rocket went. I think this must have been a bit of a fluke, this particular launch. But if you actually run the model with sensible parameters, we reckon it went up about 60 meters in the air. I think that might be slightly excessive, but it could have been 50, and could have reached an enormous velocity at the point where it's basically just about to remove its water. Now, you might argue some of these numbers are ridiculous. So according to this, the maximum acceleration is 731 meters per second squared. So I think this is possibly unlikely. But, remember, you've got a very, very low mass rocket. So the acceleration could be very large. And of course, then it tops out at g as it's falling. So in other words, you can work out all the parameters, and then you can kind of rejig those until you've got something which you think is physically realistic. So the last one is rather fun. So this is called roll the loop. So what we've got is a kind of sphere here which rolls down a circular course and sort of keeps going around. And the idea is that if the height is greater than this quantity, so what you'll do is you'll roll all the way around without falling off. But the best example is what happens what height can you have? So the sphere or cylinder, doesn't really matter which one you use, will basically come off the sort of wall, fall as a projectile and land exactly at 0, 0. And that's the trajectory you can see. So it turns out that 7 plus this lot, so K is the radius of the cylinder, R is the radius of the loop. Rho is, 1 or 0, depending if it's rolling or sliding, and sigma depends if it's a cylinder or a sphere. Okay, so I wonder if I can actually run this simulation. Hope I've got it. Let's have a look. So MATLAB, what we want is code, physics, rotational dynamics, loop the loop. Actually, I think it's roll the loop, actually. Let's go up a bit. There you go. And I can't remember which model I've got for this one. We'll soon find out. Let's have a look. So there we go. It's rolling. So this is a dynamic solution. We've got a kind of trail going on. So I'm updating this. I think this is going to fall off, I reckon. Oh, I know. I think this is one that's going all the way around. There we go. This will be a pretty one. There we are. So there we go. That's one we've got an animation as well. There we are. It starts again. So in this case, you might want a sort of trail. So what is the path of a spot on my cylinder as it rolls? And if we get it to fall off, let's have a little look. So make it all around. So land, there we are. So if I comment out this bit, this is the right height to make it go all the way around. So I'm going to just run that, and then I think we'll be done. So there we go. So this is not going quite as fast now. So it will, I think, get to about here, and hopefully it will fall off and then become a projectile. There we go. It's still rotating, of course. We're ignoring air resistance, and it will land precisely at the bottom. There you go. Or rather, yes. So there we are, the edge of the sphere. Right. I think we'll stop there. Hope that was fun. Again, as the idea here is to just give you some inspiration of the sort of things to do. So if you've never programmed before, don't start with roll the loop. I would probably start off with a calculator. So where's my double ball bounce? Something like this. Here we go. You could even do a speed, distance, time calculator. But the point is, put the illustrations in, make it interesting. Second thing you might want to do is use a loop to look at some kinematics. We looked at the ball bounce, because you can work that all out yourself, or perhaps something more complicated. You could have ball bounce with air resistance, for example, all sorts of things. So I hope that was fun. Thank you very much for coming. Next week will be on something a bit different. What have we planned? Lena, is it gravity next week? Maybe we'll just set it to be that way.
Andy, can I just say something?
Yeah.
Yeah, just because we've been getting a lot of questions, I just want to clarify. So those seminars are mostly explaining how you get a physical phenomenon and how you start thinking about it to build a model to describe it, right? So it's more so this
right.
kind of thing. You won't go into details of exactly how to write code and the syntax and so on. The challenge itself, it goes in stages, so it's very inclusive. It's technically building one model, but the first stage of the challenge, you start literally in Excel. So if you haven't done any coding, you can still attempt it. And how it's graded is, as I said, there's multiple stages, and however far you go, you get bronze, silver, gold, whatever. And if you do something exceptional, like build an app, whatever, if you actually code, then we have like a special category at the top. But the point is, you don't need to know about classes and types of variables and whatever. Just start thinking about how to translate the physical world into a model, which is what those webinars are helping you with. And afterwards, you're going to figure out either Excel or simple Python or simple MATLAB or whatever you want. Okay.
Right, absolutely. So this is inclusive for everyone. Really, if you think about the goal of the Physics Olympiad itself, we are trying to get the sort of top 4 or 5 to go to represent the United Kingdom at the International Physics Olympiad. But the vast majority, the thousands and thousands of people who do BPHO, the idea is to access the good physics, to have a good go at some problem solving. That's our major purpose. And this challenge. So we want you to use this as a way into, really, to master your physics, to really enjoy yourself. And we're going to do this by, setting challenges and learning to do some coding. So if you've never done it before, start with Excel, build a calculator.
Yes. And on that, Andy, is there a sort of little bit of prep? Are there some examples that they are encouraged to do in the download of the paper? Well, there's a 70 megabyte download of all this stuff.
So what we'll do is, I think if I can bring up the Eclecticon just very briefly, and I'll show you the resources. I will update them actually. So let's go for this one.
And whilst Andy's doing that, a few people have sort of been a bit daunted by the amount of material. This is an hour's presentation of several weeks' work. So don't feel like you've got to take all this in. This is showing you ideas. This is to excite you about things that you could do. And that would be, I don't think that's my computer. That would be a small piece of this, which you would develop a little bit. So don't get put off by the sheer volume. This is just to show 10 examples.
Yeah, absolutely. And really, a single app, might take you, months of development. That's kind of the idea. In fact, I've shown you that a calculator might take me an hour or so, or perhaps a bit less to count, maybe a few minutes. Whereas, the app of the rolling of the loop, that took me a long time to figure that out. The sort of the app with the sort of sliding cat, that was quite a lot of work. So, wherever you are level wise, try something out. And if you've not done anything before, do the simplest thing you can do, which actually puts a model together. I'd recommend using Excel for that. But absolutely, it's not about the coding, it's about the physics. And you want to start off with a piece of paper just in the normal way of creating your models. So I think maybe something to use. This is my Eclecticon website. I've actually got the challenges for 22, 23, and 24 here. I think maybe a good idea just to briefly show you one of these. So I think if I just download that, if I open that up, there we go. So this one, here we go. So this is the challenge pack for last year. So we give you this, and you've got some graphs. If I sort of see one of these, so this is the very first challenge. So you may think, oh look, I recognise that. That's in Excel, absolutely. So you've got a projectile launched. We've got a graph of the motion. You can see the little circles, which is what happens at a certain time step. So we fixed the time step here. We've got all our inputs like the launch angle.
Are you projecting your screen?
Oh, well, yeah, no, I'm not. I will do that again. Hang on a minute, bear with me. Right, there we go. Share screen. There we go. Thanks very much, Robin. So there we are. Hopefully you can see that. So where have I got this from? So this is on the Eclecticon. Let's see where that is. I've actually put that there still. All right. So this is my website. If you go to physics, you go to BPH. Actually, probably courses is a good idea. Computational challenge. This is one of the challenges. These are little zip files. You can also download all the presentations like today, for example, and the apps and the code. I update those semi-regularly, but pretty much everything you'll have seen today, you can download yourself. But if you want to run it, you'll need to get MATLAB. So where was I? So the computational challenge one, where is it? It is, here we go. It's a PDF, isn't it? Yeah. So this is the very first challenge. So you're going to create a simple model of drag-free projectile motion. And basically, you're plotting this graph. Here we go. Here's the X and Y and the velocities. And you can do that in Excel. Or you could code it up. But, that's the very first challenge. And so in this particular one, it builds. So the very last challenge, for example. So let's find the last one. So here we go. Well, this is the extension idea. So you've launched a projectile from, I think it's like in Belgium, and it's landed in the Indian Ocean. But you're incorporating the rotation of the Earth, and it's all in 3 dimensions. And you've got gravity, which works with Newton's laws, all that kind of stuff. So that could be done in an app, whereas the first one you can do in Excel. So here's another app of projectile motion. So it kind of builds really. Those are the extension things. And that's what was the 10th challenge? There we go. So challenge number 9 is to sort of work out projectile motion, but with drag. All right. So we stage it. So if you want to get a bronze, you can do everything in Excel, most of the challenges. But if you want to get into the high golds, you really need to get into programming and make apps and all sorts of fun stuff. Okay. Any more questions?
Yeah, we're doing okay with the questions, no worries.
Can I ask a question, which is what should students do between this week and next week? So do you have anything that you think they should get on with?
Yeah, absolutely. So I think what I would do, so maybe to sort of download one of the challenges from the last 3 years. Pick one what you think looks interesting to you, and maybe sort of have a go at the very first task. You'll know where you are. Some of you will be expert programmers, and some of you will be completely new to this. So pick something simple. In both cases, it will be a confidence builder. I think that would be good. And of course, we've been looking at models of motion. So you could download the presentation for today, and you could have a go yourself. You could download my code, but I think it'd be much better to maybe, if you take the bouncing ball problem, that's a classic physics problem that all of you will encounter at some point in your education. So, can you have a go yourself? You could use my code, or you could, write it in a different language. That's the sort of thing I would probably do. But pick one thing, do it well. Allocate an hour or two on a Sunday afternoon, with a nice cup of coffee. Other beverages are available. Maybe find a friend and just have some fun with it. Don't treat this as a stress-making exam thing. You've got to be assessed. Just have a go, and you'll struggle. Things will be wrong. You'll make some syntax errors, but suddenly it will work, and you will have created something. And that's a really good feeling. And that's how you're using your physics. So yeah, get stuck in, have a go, see what happens.